The word problem in the computational mathematics is the problem of deciding that the two expressions are equivalent with respect to a set of overriding identities. A deep result of the computational theory is that answering these question is in many important cases undecidable. For example, in the computer algebra, one often wishes to encode mathematical expressions using an expression tree. But there are often multiple equivalent expression trees. So we have some, for example, number, and we can present it as different expressions. And this question naturally arises of whether there is an algorithm which given as an input two expressions and decide whether they represent the same element. Such an algorithm is called a solution to the word problem. For example, imagine that we have the symbols x, y, and z, and they represent real numbers. And they have two expressions, one of which is look like this, and the second is look like this. And we need to write some computer program which take to these expressions and say to us produce if they equal, it produce equal, and otherwise it produce not equal if they not equal. For example, for these two expressions, it will produce not equal. The most direct solution to a word problem is to take the normal form of the expression. So if they take all the expressions, we group into equivalent classes, and they pick up some normal form element from the equivalence class which represent this equivalence class. And after this we take these two normal forms and compare them with synthetic equality. What is synthetic equality? So there are two notions of equality for mathematical expressions. The first is the synthetic equality and the second is the semantic equality. Synthetic equality is the equality of their representation in the computer. So here actually we have the one same object and it can be represented in a different representations. And in the terms of synthetic equality, this will be the different objects. But of course, in the terms of semantics equality, this will be the same object, because these two expressions represent the same mathematical object. And the mathematical object is something that is like a Platonic idea sitting inside our head. But it is not representation somewhere in the some data structure on some other encodings. And there is a Richardson theorem that says that there may not exist an algorithm that decide that the two expressions representing numbers are semantically equal if exponential and logarithms functions are allowed in the expression. Accordingly, semantic equality may be tested only on some classes of expressions, such as polynomials and rational fractions. So, this means that we not always can say that these two expressions are equal or not. So there must be some constraints on these expressions when they can say that they equal. And the word problem can be extended into the unification problem. And while word problem asks whether two terms t1 and t2 containing constants are equal. On the other hand, a proper extension of the word problem, known as the unification problem, asks whenever the two terms t1 containing variables have instances that are equal, or in other words, the equation t1 equal t2 has any solutions. So, for example, here we can see the word problem. It's just need to provide to us some Boolean value. If these two expressions represent the same term or not. And here we can see the extension of this problem, and this is a unification problem. You can see that you have a variable x here, and in this situation it is not enough to say true or false. We need to provide some solution for our x here. Okay. And of course here the concrete solution is x. If they provide x as a free, they can say that these two expressions are equal. The word problem also exists for semi-few systems. The accessibility problem for string rewriting systems or the semi-few systems or semi-groups can be stated as follows. Given a semi-few system, G and two words, so two strings, which belongs to this system. Can U be transferred to D by applying rules from R? Note that the rewriting here is one day. The word problem is the accessibility problem for symmetric rewrite relations, i.e. few systems. And this problem is undecidable. There is no general algorithm for solving this problem. This even holds if they limit the systems to have finite representations, i.e. finite set of symbols, and a finite set of relations on these symbols. Even the word problem restricted to ground terms is not decidable for certain finitely presented semigroups. What is a ground term? The ground term is a term that contains no variables. Ground terms may be defined by logical recursion, formula recursion. Elements of C are ground terms. So C is the set of constant symbols. So this is a notion of the first order language. And the ground term of this language is, so we can have some constants and we can some n-ary function, and this also be the ground terms. And every ground term can be given by a finite application of these two rules, so the constants or the n-ary function, and there is no other ground terms, and predicates cannot be ground terms. Also, the word problem exists in the combinatorial calculus and lambda calculus. One of the earliest proofs that a word problem is undecidable was the combinatorial logic, when are two strings of combinators equivalent. When they equivalent? Because combinators encode all possible Turing machines, and the equivalence of Turing machines is undecidable it follows that the equivalence of two strings of combinators is undecidable. Alonzo Church observed this in 1936. Likewise, one has essentially the same problem in n-type lambda calculus. If the given two distinct lambda expression, there is no algorithm which can discern whether they are equivalent or not. Equivalence of lambda expressions is undecidable. For several type variants of the lambda calculus, equivalence is decidable by comparison of normal forms. So if we add somehow the types to the lambda calculus, we can decide this problem. Also, the word problem exists for abstractive writing systems. We have two objects, x and y, and they need to say they equivalent under this relation. And they know that the word problem for this IRS is undecidable in general. However, there is a computable solutions for the word problem in the specific case where every object is reduced to a unique normal form, infinite number of steps. So we have the terminating system, and every object of this system has the unique normal form. Then we can decide this problem. So in other words, the system is convergent, and two objects equivalent under this relation if and only if they reduce to the same normal form. And there exists Knuth-Bendix completion algorithm, which can be used to transform a set of equations into a convergent term rewriting system. So this algorithm can transfer a set of equations or the terms into a confluent term rewriting system. And when the algorithm succeeds over this term rewriting system, it effectively solves the word problem for the specified algebra. So where they define these equations over terms. And the solving of the word problem, deciding if the x is related to y in this rewriting system, usually requires heuristic search. While deciding x normal form equal y normal form is straightforward. So we just do the reduction steps. So let's look here. We have so by this gray arrows, the see that the find the normal forms here. Just do the reductions from this and these points, and to find the relation between these 2 points, we need to heuristic search, which will find this actually green connection, and there are many red connection, red paths which show that we can't connect them with these paths. And also the word problem exists in the universal algebra and in the it can be applicable in for free lattices. Okay.